Hello viewers, welcome to CEC Gurukul lectures. In my last interaction with you, I had discussed the interaction of optically active compounds with plane polarized light. Picking up the strings from there, today I shall be discussing work of pioneers of this field which led to the idea of stereochemistry, or which laid the foundation of stereochemistry and optical isomerism. I shall be discussing work of 5 pioneers, starting with work of Biot. Biot worked with inorganic substances and showed activity in crystalline form. Louis Pasteur, who was a great scientist and father of microbiology, laid the foundation of stereochemistry. Johannes Wislicenus said that the optical activity of these compounds cannot be shown only on the basis of their structural formulae. Van 't Hoff and Liebel correlated chirality with tetrahedral structure of the molecule. Now I shall be discussing work of each scientist in detail. French physicist Biot in 1813 showed that some inorganic substances like quartz, rock crystals and crystals of potassium chlorate, potassium bromate and sodium periodate showed optical activity in crystalline form. But these compounds did not show optical activity when they were ground, fused or dissolved in a solvent. Therefore, Biot concluded that the optical activity of these compounds was due to their crystalline structure, which was destroyed when the compound was ground, fused or dissolved in a substance. But later on, Biot, while working with organic compounds, found that camphor, tartaric acid and turpentine oil showed optical activity in liquid and gaseous states and even in solution. He found that while working with tartaric acid in 1835, Biot showed that tartaric acid is dextrorotatory. That is, when he passed the plane polarized light in a solution of tartaric acid, what he found that these solution turned the plane of plane polarized light in right hand direction. From this he concluded that this particular sample was dextrorotatory. Whereas when he again working with tartaric acid in 1838, he showed that the same tartaric acid did not change the path of plane polarized light. So this is where we see that when the rays is entering the sample and the one which is emitting, those are vibrating in the same direction. That is, there was no change in direction of the plane polarized light after it was passed through the sample of tartaric acid. He could not explain this, that as to why this was happening. But later on it was established that maybe this was a racemic mixture and it was defined as equimolar mixture of 2 enantiomers. That is, that it contained equimolar of dextrorotatory and levorotatory that were present in 50-50%. Therefore, he then suggested that the optical activity of an organic compound was a molecular property which was even retained in solution. So he concluded on basis of these experiments that optical activity was due to constitution of an organic compound rather than its crystalline structure. This was followed by work of Pasteur. Pasteur also worked with tartaric acid, and he carried out number of experiments. In 1846, Pasteur observed that the tartaric acid which he had obtained by fermentation of grape juice rotated the plane of plane polarized light in right hand direction, and he said this molecule or this acid is dextrorotatory. But at the same time, he obtained an acid from mother liquor, which was left in the purification of acid, and this acid which he obtained from mother liquor after the purification of acid, he found was optically inactive. He was perplexed as to why was this happening. So he carried out further investigations. For that, he prepared the sodium ammonium salts of both the acids, that is the one which he had prepared from the grape juice by fermentation of the grape juice, and one which he had obtained from the mother liquor. And what he found, that the salts which he had obtained from mother liquor had different types of crystals. He had very meticulously separated the crystals which were found in mother liquor with help of forceps and a magnifying glass. And what he found, that one crystal was exactly similar to the crystals of the D form. He then compared the crystals and he found these crystals were similar. But on the other hand, the arrangement of facets in the other crystal were in such a way as if they were mirror images of the first. So the tartaric acid which he had obtained from mother liquor had two types of crystals. One was having a right facet, that is this is having a right facet crystal, and this was the left facet crystal. And what he found, that the right facet crystal was rotating the path of plane polarized light in right hand direction, whereas the left facet crystal was rotating the path of plane polarized light in left hand direction. So he concluded that the right handed facet crystals were dextrorotatory, whereas left-handed facet crystals were levorotatory. He further made a solution of these two crystals in which he took equal mixture of left-handed and right-handed crystals and dissolved them in water. And surprise again, this solution did not show any optical activity. He called this solution a racemic form. So Pasteur had discovered the racemic form of tartaric acid, and he also developed the science of racemization, that is the process of racemization. That is, racemization is a process when two enantiomers of an isomer are dissolved in equal amounts. They cancel the optical rotation because of one another, as a result of which the net result is that that particular mixture will be optically inactive. So he found that when he compared the other physical properties of these two crystals, he found that both of them had the same melting point. But the difference was, one was levorotatory and the other was dextrorotatory. So Pasteur proposed that since the crystals of tartaric acid were mirror images of each other, their molecules were also mirror images of each other. This is what we've shown here, which was discovered later on, that these two enantiomers of tartaric acid or optically active isomers of tartaric acid are mirror images of each other. So now Pasteur reasoned that this optical activity which is shown by tartaric acid is because of the dissymmetry of the crystals, and this dissymmetry of the crystals was due to dissymmetry of the component molecules, and these were the molecules which were responsible for the optical activity. Now, since I have already discussed that these two enantiomers had the same physical properties, that is, they had the same melting point, boiling point, their densities were same, they were only rotating the path of plane polarized light in different direction. But in his further experiments, Pasteur found that these two compounds of tartaric acid, that is the D molecule and the L molecule, had different biological activities, because it was only when he fed the racemic mixture to microorganisms he found that they fed on only one isomer. So he said that the biological properties of these molecules are different. It is, and he says that this difference in biological properties of the molecules depends not only on the nature of the atoms which are comprising the molecule, but decides on the manner in which these atoms are arranged in the space. So he said that because of the same atoms, the value of rotation will be same, but because of the different orientation of the groups in molecule in space, its interaction with plane polarized light will be different, and they will rotate plane polarized light in different directions. And today we also now recognize that Pasteur was the one who had made the first resolution of racemic mixture by a mechanical method. Although now we have much advanced methods, one of them is asymmetric synthesis, which I shall be discussing later. And he laid the foundation of chemistry, what we now call as stereochemistry. Later, Pasteur in 1853 discovered fourth form of tartaric acid, which was also optically inactive, and it was named the mesotartaric acid. Its chemical formula was similar to the racemate, but the irony was that the mesotartaric acid could not be separated into D and the L forms. Now, this Pasteur's work was followed by work of Wislicenus. Wislicenus in 1873 reported three forms of tartaric acid, of lactic acid, the D form, the L form, and the racemic form. So here I have shown the structure of tartaric acid, in which it is 2-hydroxy propanoic acid. That is, we have 3 carbons and OH is attached to the second carbon. So when he discovered that the 2 isomeric lactic acids had identical chemical structure, but they had different physical properties, so he came to the conclusion, or he argued, that ordinary structural formulas were inadequate to explain the difference as to how this molecule is rotating plane polarized light in 2 different directions. That is, if he was taking D lactic acid, it was rotating plane polarized light in right hand direction, Whereas if he did the experiment with levulactic acid, he found that this acid was rotating the plane of plane polarized light in left hand direction. So he said that this structure, which I have already shown here, this structure is not enough to explain as to how this molecule and why this molecule is rotating the path of plane polarized light. So he concluded that this molecule should be represented by a three-dimensional formula which will indicate the different arrangement of atoms in molecule in space. And he called this type of isomerism as geometrical isomerism. So the hypothesis of Pasteur and Wislicenus was supplemented by another set of pioneers, that is Van 't Hoff and Liebel. Work of Van 't Hoff and Liebel, which they conducted in 1874, eventually led to the discovery that tetravalent carbon atoms are tetrahedral. That is, if this is a sp3 hybridized carbon, then the atoms which are attached to this, supposing we say this is the structure of methane and it is attached to 4 hydrogen atoms, so these will be arranged in a tetrahedral form around this carbon. Here I have represented the two-dimensional structure of a three-dimensional molecule. This line is the line, it is indicating the bonds which are in the plane of the paper, whereas broken line is indicating the bond which is in the paper away from the observer, and the wedge is indicating the bond which is coming out of the plane of the paper towards the observer. And this representation I will be using in most of my lecture today. So now what happened after they proposed? But the question was, how did they come to the conclusion that this tetravalent carbon has a tetrahedral geometry? So this work was proposed, that is by Jacob Van 't Hoff, while he was a student and he was only 22 years old. And incidentally, Van 't Hoff also received the first Nobel Prize in chemistry. Now Van 't Hoff suggested his theory that the structure should be tetrahedral on the basis on the study which he carried while doing the reaction with methane, and by converting methane into monosubstituted, disubstituted products. And he found out his evidence was based on the number of isomers which were formed when he converted methane into monosubstituted methane, disubstituted methane, trisubstituted methane and tetrasubstituted methane. So first of all, Van 't Hoff realized that the 4 carbon atoms in methane had to be equivalent. That is, the carbon hydrogen bond is going to be the same, the bond length will be same, the bond angle between these bonds has to be same. So when they said that they are equivalent, so he proposed different structures for this molecule. One was a geometrical square, other was a trigonal pyramidal, and the third one was a tetrahedral structure. He discarded the geometrical square because he said that if he was considering a geometrical square to be structure of methane, it will not be able to justify the one isomer which will be formed if we carry out disubstitution of methane. If it was a geometrical isomer, then the number of isomers formed or represented would be 2, whereas this molecule can be just represented by one structure. So therefore he proposed that the central tetrahedral carbon center. So he said that tetrahedral carbon not only explained the absence of isomers in di-substituted methane, but they also predicted the existence of mirror image isomers, because it is only when the molecule has a tetrahedral geometry it will lead to a mirror image. Now this mirror image may be superimposable or it may be non-superimposable. In this case, in case of methane, the mirror image is superimposable. So on the basis of tetrahedral structure, Van 't Hoff and Liebel in 1874 explained the activity of the compounds, that is the optical activity of the compounds, and they correlated chirality to tetrahedral structure of the molecule. They said when the 4 valencies of carbon atom are directed towards 4 corners of a regular tetrahedral with 4 different groups at the 4 apexes, there is possibility that 2 different arrangements will be there, and which will be non-superimposable mirror images of each other. So he considered that if an organic compound having general formula CABDE, where C is the tetrahedral carbon or the central carbon, and it is attached to 4 groups which are different, that is A, B, D and E. So he said that if this is the molecule, the chemical general formula of the molecule, then this molecule will always give 2 isomers and both will be optically active. So here on your screens you can see that I've shown you the tetrahedral structure of 2 molecules, and in this case 1, 2, 3, 4, all the 4 groups are different, and when we compare the mirror images of 2, we find that they are non-superimposable mirror images of each other. So both these molecules will be optically active. So I have summarized here, I have discussed here the work of 5 scientists which led to the concepts of stereochemistry, that is chirality. Now we shall be discussing chirality and its relation to optical activity in my next lecture. Thank you.